Today we're going to explore one of the most remarkable stories in 20th century physics, the discovery of Bose-Einstein statistics and the prediction of a completely new state of matter. This story involves two physicists, Satyendra Nath Bose, a relatively unknown Indian physicist working in Dhaka, and Albert Einstein, already famous for his theory of relativity. Bose was born in 1894 in Calcutta. Einstein was already a towering figure in physics by the 1920s. Their collaboration would change our understanding of matter-its. To understand their breakthrough, we need to go back to the problem of blackbody radiation. This was the puzzle that launched quantum mechanics. A blackbody is an idealized object that absorbs all radiation that hits it and emits radiation based purely on its temperature. Think of a hot piece of metal glowing red, or the filament in an old incandescent light bulb. The blackbody absorbs all incoming light and re-emits it based on temperature. The question is, what is the spectrum of this emitted radiation? Classical physics, using Maxwell's equations and statistical mechanics, predicted that a blackbody should emit infinite energy at short wavelengths. This was called the ultraviolet catastrophe, and it was completely wrong. In 1900, Max Planck found an empirical formula that fit the experimental data perfectly, but his derivation was awkward and relied on introducing the quantum of energy, E equals h nu. Energy equals Planck's constant times frequency. This was the birth of quantum theory. Planck's radiation law gives the energy density at frequency nu and temperature T. This formula works, but Planck's derivation was unsatisfying because it mixed classical and quantum ideas. The key issue is how to count the number of ways photons can be distributed among energy states. This is a statistical mechanics problem. In classical statistical mechanics, particles are distinguishable. If you have two particles in two boxes, there are four different arrangements because you can tell particle 1 from particle 2. State 1, both particles in box 1. State 2, red in 1, green in 2. State 3, green in 1, red in 2. State 4, both in box 2. That's 4 distinct arrangements because the particles are distinguishable. This counting leads to Maxwell-Boltzmann statistics, which works well for classical gases at high temperature. But here's the critical insight that everyone missed. Photons are fundamentally indistinguishable. There's no way to label one photon versus another photon of the same frequency. In 1924, Bose was teaching Planck's radiation law to his students in Dhaka. He realized that the classical counting was wrong for photons. Bose's key idea was to count the occupation of states rather than permutations of particles. If particles are indistinguishable, then only the occupation numbers matter. Now, if the particles are identical, we can't distinguish the case where red is in 1 versus green is in 1. We only have 3 distinct states, both in box 1, 1 in each box, or both in box 2. This seemingly small change in counting has profound consequences for the statistical distribution. Let me show you how Bose's counting directly gives Planck's law. We'll do a simplified version of his calculation. First, we need to count how many photon states exist in a given frequency range. This comes from the phase space volume in momentum space. The number of photon states in frequency interval d nu is 8 pi v nu squared over c cubed times d nu, where v is the volume. The factor of 8 comes from 2 polarization states. Now we need the probability that a state of energy h nu is occupied. With Bose counting, we get a different distribution than classical. The average occupation number is 1 over e to the h mu over kt minus 1. This is the Bose-Einstein distribution. Notice the minus 1 in the denominator, not plus 1. The energy density is the number of states times the energy per photon times the occupation. Energy density equals the density of states times h nu times the average occupation. When we substitute everything, we get exactly Planck's radiation law. Bose derived it directly from first principles just by counting photon states correctly. Bose sent this paper to Einstein in June 1924. Einstein immediately recognized its importance, translated it to German himself, and got it published. But Einstein didn't stop there. He asked a profound question. What if we apply Bose's counting to massive particles? not just photons. At first it seems crazy. Atoms have mass, they move slowly, we can in principle track them. How can they be indistinguishable? But quantum mechanics tells us that all identical particles, whether photons or atoms, are fundamentally indistinguishable. There's no hidden label on an electron or an atom. In late 1924 and early 1925, Einstein wrote 2 papers extending Bose's method to a gas of massive atoms. Unlike photons, the number of atoms is conserved, so we need to introduce a chemical potential mu. This changes the distribution slightly. The occupation number is now 1 over e to the epsilon minus mu over kT minus 1, where epsilon is the energy of the state and mu is the chemical potential. Now comes Einstein's stunning prediction. He calculated what happens as you lower the temperature of this quantum gas. At high temperature, the gas behaves classically. The atoms are distributed over many energy states according to the usual thermal distribution. But below a critical temperature, something extraordinary occurs. A macroscopic fraction of the atoms suddenly drops into the lowest energy state, the ground state. At high temperature, atoms are distributed among many energy levels. Each state has a few atoms, following thermal statistics. Below the critical temperature, a macroscopic number of atoms pile into the ground state. This is Bose-Einstein condensation. The bulk of atoms now occupy the same quantum state. Let's calculate when this happens. What is the critical temperature for condensation? The critical temperature is 2 pi h bar squared over mk times the quantity n over 2.612 to the 2/3 power, where n is the number density and m is the atomic mass. Let's plug in numbers for rubidium-87, which was used in the first experimental realization. Let's say the density is 10 to the 14 atoms per cc. The mass of rubidium-87 is about 87 atomic mass units, which is 1.45 times 10 to the minus 25 kilograms. The density is 10 to the 20 per cubic meter. When we calculate, we get a critical temperature of about 200 nanokelvin. That's 200 billionths of a degree above absolute zero. Incredibly cold. Why is this temperature so low? Because at higher temperatures, the thermal de Broglie wavelength is smaller than the spacing between atoms, so quantum effects don't matter. The thermal de Broglie wavelength is h over the square root of 2 pi mkt. This is the quantum wavelength associated with an atom at temperature T. Bose-Einstein condensation happens when the thermal wavelength becomes comparable to the interparticle spacing. Then the atom's quantum wave functions overlap and they must be treated as indistinguishable quantum particles. Einstein published this prediction in 1925, but for 70 years, nobody knew if it was real or just a mathematical curiosity. The problem is that as you cool a gas, the atoms attract each other and form a liquid or solid long before reaching the condensation temperature. So it seemed impossible to observe. The breakthrough came in the 1990s with laser cooling and magnetic trapping. Scientists learned to cool dilute gases of alkali atoms to nanokelvin temperatures without them solidifying. In June 1995, Eric Cornell, Carl Wyman, and their team at GILA created the first Bose-Einstein condensate using rubidium-87 atoms. They cooled a cloud of about 2,000 rubidium atoms to 170 nanokelvin. Suddenly, a dense core appeared in the velocity distribution. This was the condensate. Above the critical temperature, you see a broad thermal distribution. Below the transition, a sharp peak appears at zero velocity. That's the condensate, macroscopic occupation of a single quantum state. The condensate has remarkable properties that confirm it's a new state of matter. All atoms in the condensate occupy the same quantum state. They're described by a single macroscopic wave function. The condensate is a coherent matter wave, like a laser is a coherent light wave. You can observe interference between two condensates. The condensate flows without friction. It's a superfluid. If you stir it, it forms quantized vortices instead of turbulent flow. Now let's address an important question. Why do some particles obey Bose statistics and others don't? In quantum mechanics, particles are classified by their spin. Particles with integer spin are bosons. Particles with half-integer spin are fermions. Bosons have spin 0, 1, 2, and so on. Examples include photons with spin 1, helium-4 atoms with total spin 0, and the Higgs boson with spin 0. Fermions have spin 1/2, 3/2, and so on. Examples include electrons, protons, neutrons, and helium-3 atoms. Bosons obey Bose-Einstein statistics. Multiple bosons can occupy the same quantum state. In fact, they prefer to bunch together. Fermions obey Fermi-Dirac statistics. The Pauli exclusion principle says no two fermions can occupy the same quantum state. This is why electrons fill up atomic orbitals one by one. The Bose-Einstein distribution has -1 in the denominator. The Fermi-Dirac distribution has +1. This +1 enforces the exclusion principle. The occupation can never exceed 1. The spin statistics theorem, proved by Wolfgang Pauli in 1940, shows that this connection between spin and statistics is a fundamental consequence of quantum field theory and relativity. Since 1995, Bose-Einstein condensates have become a major research area with many applications. BECs can simulate other quantum systems. You can create artificial crystals, study quantum phase transitions, and test theories that are hard to explore otherwise. BECs enable ultra-precise measurements. Atom interferometers using BECs can measure gravity, rotation, and fundamental constants with record precision. BECs are being explored for quantum computing and quantum communication. The coherence and control possible with BECs makes them promising for quantum technologies. BECs let us study strongly interacting quantum systems in a controlled way. We can dial the interaction strength, the dimensionality, and watch quantum phase transitions in real time. Let's step back and appreciate the deep lesson from this story. In classical physics, every particle has an identity. You can paint them different colors and track them. Statistics follows from counting permutations. In quantum mechanics, identical particles have no individual identity. There's no such thing as this electron versus that electron. Identity is not a fundamental property. This seemingly philosophical point about identity has concrete physical consequences. It changes how we count states, which changes statistical distributions, which predicts new phases of matter. Let me give you an analogy to help grasp this. Imagine you have coins with serial numbers. You can say coin number 457 is in my left pocket, and coin number 983 is in my right pocket. These are distinct arrangements. Now imagine all the serial numbers are erased. The coins are perfectly identical. Now all you can say is, one coin is in the left pocket and one is in the right. You can't distinguish the case where they swap pockets. This indistinguishability reduces the number of distinct configurations, which changes the entropy and the statistical distribution. That's the essence of Bose's insight. Let's do a quick back-of-the-envelope calculation. How many atoms are typically in a BEC? Typical BECs contain 10,000 to 10 million atoms. Compare that to Avogadro's number, 6 times 10 to the 23, and you see these are tiny samples. At temperatures well below the critical temperature, more than 90% of the atoms can be in the condensate. It's truly macroscopic quantum coherence. A laser has perhaps 10 to the 15 photons in the same quantum state. A BEC is like a matter wave laser, but with far fewer particles. Here's an interesting historical question. Why didn't Bose share the Nobel Prize for this work? Einstein was already too famous to get another prize for this. But what about Bose? Unfortunately, Bose never received the Nobel Prize. Some historians think it's because the significance of his work wasn't fully appreciated at the time. He was working in colonial India, far from the European centers of physics. However, Bose's name is immortalized in physics. Paul Dirac coined the term boson to honor Bose. Every time we talk about photons, gluons, or the Higgs boson, we're honoring Satyendra Nath Bose. Let me briefly mention some modern extensions of these ideas. In 2003, physicists created the first fermionic condensate. Fermions can't condense directly, but pairs of fermions can form bosonic molecules that then condense. This is related to superconductivity. In semiconductors, an electron and hole can bind to form an exciton, which is a boson. These can condense, creating exotic quantum states in solid-state systems. In 2010, physicists created a Bose-Einstein condensate of photons in an optical microcavity. This is remarkable because photons don't usually conserve number, but the cavity thermalization changes this. Polaritons are hybrid light matter particles. They can condense at much higher temperatures than atoms, even room temperature in some materials. Let me show you one more piece of mathematical beauty in this theory. The partition function for a Bose gas is the product over states of 1 over 1 minus e to the minus epsilon over kT. This elegant formula encodes all the thermodynamics. For a Fermi gas, it's the product of 1 plus e to the minus epsilon over kT. The difference between plus and minus captures the profound difference between fermions and bosons. Let me summarize this remarkable chain of ideas. First, classical statistical mechanics failed completely to explain blackbody radiation. The ultraviolet catastrophe showed something was deeply wrong. Second, Bose realized that photons must be counted as indistinguishable particles. This gave Planck's law directly and naturally. Third, Einstein recognized this wasn't just about light. All identical particles, including atoms, must be indistinguishable. Fourth, this led to the prediction of Bose-Einstein condensation, a completely new state of matter where quantum mechanics becomes visible on a macroscopic scale. Fifth, after 70 years of technological development, this prediction was confirmed experimentally. Finally, today BEC is a thriving research area, with applications from fundamental physics to quantum technology. There's a deep philosophical point here about the nature of identity. In quantum mechanics, the identity of individual particles is not a fundamental property. What's fundamental is the quantum field and its excitations. The particles we see are just quanta of these fields. This dissolves our classical intuitions about counting and individuality. You cannot ask which atom is in the ground state when you have a condensate. The question is meaningless. Yet this abstract philosophy leads to concrete predictions, critical temperatures, occupation distributions, interference patterns. Philosophy becomes physics. The story of Bose-Einstein statistics is one of the most beautiful in physics. It shows how a single conceptual shift, recognizing indistinguishability, can cascade into predicting entirely new phenomena. It connects the most microscopic quantum mechanics to macroscopic observable phenomena. A change in how we count states at the particle level leads to a visible phase transition. It reminds us that great physics comes from everywhere, not just the famous centers. Bose and Dhaka, working with limited resources, changed our understanding of nature. Thank you for joining me on this journey through quantum statistics, Bose-Einstein condensation, and the quantum nature of identical particles. This is physics at its most profound and beautiful.